Hi everyone, welcome to the second lecture of this module 4 where we are discussing interface circuit for microsensors and nanosensors. In our previous class we were discussing voltage follower circuit using op amp, and we have seen that in a voltage follower circuit we do not have a feedback resistance, right, or the output is exactly following the input voltage. Okay, we have also seen that the input impedance of this voltage follower is very high, it has a unity gain, and it has a small value of output resistance, or output impedance is very low. Okay, it can also act as a current amplifier. Okay, so we have discussed at large that what are the applications of op amp, or how we can use op amp for signal conditioning of signals from the microsensors and nanosensors. Okay, there are we have seen at large that op amp can be used as a summing amplifier, it can be used for as a subtractor, as a differential amplifier, as well as an integrator. Okay, beyond that there are multiple applications, and it depends on how you are connecting the feedback and how you are giving the input. Okay, I am giving one more example that how a op amp using a diode can be used as an active rectifier. Okay, so this is a typical circuit for op amp acting as a rectifier. You can see that when you have this V1 at its input and this diode connected over this in the output of this op amp. Okay, this V naught can be written as Rf plus R1 by R1, where Rf is your feedback resistance and R1 is the resistance at this inverting terminal. Okay, so Rf plus R1 by R1 into V1, which is the regular output, minus Rf plus R1 by R1 into AOL. Okay, and whole multiply by cut-in voltage of diode, which is 0.7 for this particular diode. Okay, similarly you can use it for this op amp as a logarithmic converter. Like this is a configuration of a typical logarithmic converter where you are not connecting any capacitance or resistance in the feedback, but in place of them you are connecting a active element, which is a diode in this feedback. Okay, and then you have a resistance here R1. So this output is equal to 1 by beta log V1 minus 1 by beta log F naught into R1, where F naught is a constant and beta is again a exponential constant. Okay, so these are various ways to connect active and passive component in a op amp. Okay, then let us see one important application of this op amp in fabricating a instrumentation amplifier, or you can understand this instrumentation amplifier as a separate unit only. Okay, so let us discuss this instrumentation amplifier, or I will call it as a IA. Okay, in little bit detail. Okay, so IA is a type of differential amplifier which has extremely high input impedance. Okay, it comes with input buffer amplifier. You can see a basic circuit of an instrumentation amplifier on this screen. Okay, there is no need for input impedance matching. Whatever be the output of your sensor, you can basically use an instrumentation amplifier. Okay, you don't need to match the input impedance here. Okay, this amplifier is suitable for this microsensors and nanosensors applications very much. Okay, its gain can be precisely set by a single either internal or external resistor. Okay, and this IA has very high CMRR. Okay, so the high CMRR of this amplifier is very useful in recovering small signals which are basically buried in the large common mode offsets and noises. Okay, this amplifiers has various advantages we will see in discussion, but it exists in various configuration. One of the configuration I have shown where the gain can be given as 1 plus 2R1 by Rg into R3 by R2, where Rg is placed over here and R1 are these two resistors, while R2 and R3 are placed over here. This part is sometimes known as first stage and this part is sometimes known as second stage. Okay, fine. So this IA, as I was mentioning, that it has a very low DC offset. The drift is very small. Okay, the noises is very low. Okay, because of its configuration and its very high input impedance. Okay, this kind of amplifier has very high open loop gain also. Okay, and very high CMRR that we have just seen now. Okay, so this input impedance very high, less DC offset, low drift, low noise, very high AOL, okay, and very high CMRR make this ideal for sensing applications. Okay, so let's see its construction in little detail. If you see this IA, it has two stages basically. The first stage offers very high input impedance to both input signals and allow to set the gain with a single resistor. Okay. Then the second stage is a differential amplifier with the output negative feedback and ground connected here. You can see this configuration. You have this output and this is connected to reference through this resistor R2. Okay, and this is your sense terminal. Okay. So as I was mentioning that a number of configuration for this IA is possible. One of such configuration is written over here, and the gain can be written as 1 plus 2R2 divided by R gain into R4 by R3, where again R4 is this resistor, R3 is these two resistances. Okay, and R2 and R gain are placed over here. Very similar configuration. I mean, it can be drawn in various configuration, but the gain remain same. Okay. So this IA is used in application where high accuracy and long term stability of the circuits are needed. Okay. So please do not get confused between the op-amp and instrumentation amplifier. You have seen that you need multiple op-amps to make a instrumentation amplifier. Okay, op-amp has a finite gain and this IA has much higher gain as compared to op-amp. Okay, in instrumentation amplifier both inputs are available for connecting the signal sources, which is not possible in op-amp. Okay, here all the required feedback components are connected to other parts of the IA rather than to its non-inverting and inverting inputs. Okay, so you do not have a compulsion to only configure or to give input at inverting and non-inverting inputs. Okay, the primary function of IA is to generate an output signal proportional to the voltage difference between its two input, and that's why we call it initially a differential amplifier. Okay, so if alpha is a gain, whatever be the delta V, you just multiply it with that and you get the output voltage. Okay, so if alpha is the gain and V plus is the input voltage at non-inverting and V negative is input voltage and inverting, your V out is basically alpha into del V. Okay, so a differential input in the amplifier is crucial for rejecting CMRR. We have already seen this even for op-amps. Okay, so IA should have actually, or any other amplifier should have a high CMRR. Okay, we have seen that the CMRR for op-amps are also very decent. Okay, even for IA it is larger. Okay, so its output signal should be unaffected by the value of this these two terminal voltages and respond only to its difference. Okay, then only the common mode signals can be rejected. Okay, so this is a basic configuration of IA and the applications of IA in detail. You can read about this instrumentation amplifier in other courses like analog circuit and others. We are only covering all these things in just 5 lectures. Okay, so apart from this instrumentation amplifier, there is one more important amplifier which is known as charge amplifier, very relevant to sensors application. Okay, because most of the sensor you talk about capacitive sensor or a piezoelectric sensor or pyroelectric sensor, the output is in the form of charge. Okay, so charge amplifiers are very crucial for sensor signal conditioning circuit design. Okay, so you can understand a charge amplifier, or I am calling it a CA, as a special class of circuit having extremely low bias current. Okay, please note that when I am telling the extremely small current, okay, if you see, current is nothing but dq by dt, okay, right. So I am talking about this dq by dt, this overall term, to be very small, or this quantization of charge at little at little distinct times. Okay, so basically it means that that's why this charge generating or this charge amplifier is connected to charge generating sensors in such a way that this bias currents are very low. Okay, as I was mentioning that these sensors are basically used to convert this charge or this quantized charge to voltage, because the next stage may be say microcontroller or a DAC card require input in the form of voltage. Okay, so these amplifiers are used to convert charge signals to voltage signals from a number of sensors, including capacitive sensors, pyroelectric sensors, and other devices, including quantum sensors. Okay, so with the quantum devices coming into picture in current era, these charge sensors or charge detectors has gained lot of importance. Okay, a typical circuit for a charge amplifier or charge to voltage converter is shown over here. You can see that you have this charge generating sensor. It can be say a capacitor, okay, or capacitive sensor. It is connected through this small r resistance, which is a small value, okay, to this capacitance, and there is a feedback resistance also in parallel. Okay, so this is a typical charge to voltage converter or a charge amplifier. Okay, so these devices generate very small charge, maybe in this charge generators generate very small charges in terms of say some picocoulomb or something like that. Okay, or maybe it can be in terms of some current, maybe if you can quantize it with time, so in terms of some picoamp or something like that. Okay, so that can be converted to a voltage signal using this kind of configuration. Okay, here capacitor C is connected to the feedback network of the op-amp. You can see here. Okay, its leakage resistance, please note that the leakage resistance of this capacitance should be much larger as compared to the impedance of the capacitor at the lowest operating frequency. Okay, that should be the condition. Okay, now if you see this configuration, this output will follow the input. Okay, or this V out is actually directly proportional to del Q. Okay, or V out is nothing but minus del Q by C. Okay, so a high quality film capacitor is usually recommended along with a good circuit board where the components are coated with conformal coating, so that these charges are not trapped inside the capacitor itself. Okay, it should reach this resistance small r, then only we will be able to measure it. Okay, then there can be some complicated structure where apart from parasitic capacitances of these sensors, there can be other capacitance of the cable. For example, this cable is connecting this transducer to the op-amp. Okay, so for precise detection you have to consider the capacitance of this cable also. Okay, so that kind of thing is shown over here, where you have a typical piezoelectric transducer which is generating Q as K into Xi or KQ into Xi, and you have parasitic capacitances, cable capacitances in parallel, and CF the feedback capacitances, and you have a RF connected in feedback. Okay, so this V naught by Vi can be written as a minus Cp plus C cable by Cf, while this output in terms of charge can be written as again V naught is directly proportional to Q, or V naught is equal to minus Q by Cf, or minus Kq into Xi by Cf. Okay, the input resistance and the leakage resistance of CF, in this case the feedback capacitance CF, okay, exhibit a steady charging of CF by the leakage current till this amplifier is saturated. Okay. However, to overcome this problem, we can use a feedback resistance RF similar to what we have seen in the previous case, okay, which is connected across this feedback path, okay, in parallel with the feedback capacitance. Okay. This prevents the small leakage current from charging the capacitance heavily. Okay. Fine. So, that is how a charge amplifier is used to sense the charge as well as to amplify that charge, okay, or to amplify or to convert that charge into voltage. Okay. Now, let us consider current generating sensor. Okay. Let us consider current generating sensor. Current generating sensor can be modeled by a simple leakage resistance R in parallel with a current source, where this current source have infinite internal resistance. Okay. This current source is having infinite internal resistance, okay, and this whole system is connected to ZL. This ZL can be, input impedance of an interface circuit, because next part will be the interface circuit itself. Okay. So, this is the model of a current generating sensor. Okay. Now, this current which is generated by the sensor can flow in two directions. It can leak through this leakage resistance, or it can flow through this input impedance of the interface circuit, right. So, either you have I naught or you have I out. Okay. Now, you want this leakage current to be minimal. Okay. So, you want it to be high resistance path basically. So, you want that all your current should flow through this load or the through this interface circuit. Okay. So, this small r should be much larger as compared to the input impedance of this this interface circuit, right, which will minimize the error, because in that condition the current flowing through this R will be minimum. Okay. Now, Ohm's law suggests that to convert this electrical current I out into a voltage, current should pass through a appropriate impedance. Okay. It cannot pass through any kind of impedance if you want to cultivate it. Okay. The voltage drop across that impedance is proportional to the magnitude of the current. Okay. This is a very simple Ohm's law. Okay. Here the current generating sensor is connected to the inverting input of a op amp, which acts as a virtual ground. Okay. So, this is your virtual ground. Voltage at the inverting input is almost equal to the non-inverting input, which is already in ground stage. Okay. Now, the sensor operates at nearly zero voltage across its terminals. Okay. So, its current defines the output voltage of the op amp, or V out can be written as minus IR, right. Magnitude can be IR, but actually you have to consider this negative sign for absolute value. Okay. So, for circuit stability, this R should be much smaller as compared to this R, feedback R. Okay. Without this resistor, at high frequencies op amp would operate near to the open loop, okay, or it will operate near the open loop, the highest open loop gain actually, okay, and this will introduce some kind of oscillation in the circuit. So, if you introduce this R, actually you are decreasing the chance of oscillation, or you are providing some kind of damping. Okay. The circuit shown over here can convert and amplify, of course, the input signal. However, its speed and response depend on two factors. One is sensor's capacitance and another is the converting resistance R1. Okay. The response of this kind of circuit to step function in a time domain plane can be written as V out is equal to IRB into 1 plus R2 by R1 into 1 minus E minus T by RC, right, where RC, this is your, this part take care the time constant. So to convert current from such sensor as piezo and pyroelectric sensors, the required range of resistors RB is of the order of 10 to 100 gigaohm. This RB for in this output, if you see, there is a multiplication term RB. RB for pyroelectric sensors and piezoelectric sensors are in some gigaohm. Okay. So it is very difficult to get this RB resistance. Okay. So usually such high values of resistors may not be available, or sometimes it is actually impractical to use this kind of resistances due to poor environmental stability. Okay. So high ohmic resistor can be simulated by a circuit known as resistance multiplier. Okay. So this you can use as a resistance multiplier, where this 1 plus R2 by R1 can be considered as a multiplier. Okay. So positive input of an amplifier is implemented by adding a positive feedback around the amplifier. Okay. So R1 and R2 in this configuration forms a resistor divider, and due to high open loop gain of this op amp, actually this V positive and V negative at these two input terminals are actually equal, and the voltage V2 can be written as R3 by R1 plus R3 into V negative, or V plus into R3 by R1 plus R3, because V negative and V positive are nearly equal to each other. Okay. Through the voltage drop, current through the resistor can be calculated as V positive minus V negative by RB, or this value IB can be given as R1 by R1 plus R3 into 1 by RB. Okay. Therefore, the input voltage is a function of the input current and the resistive network. Okay. So V positive can be written as IB into RB into 1 plus R3 by R1, and this is very important. Okay. So if you see this equation, RB is multiplied by 1 plus R3 by R1. Therefore, RB, say if you want to achieve very high resistance, RB, for example, if I choose to be say 10 mega ohm, okay, I can choose this 1 plus R3 by R1 to be 5, or the multiplication factor to be 5, okay, so that virtually I am able to achieve 5 into 10 or 50 mega ohm resistances. Okay. However, it is not like that. You can keep on increasing this multiplication factor, and usually this is kept below 10 for practical applications. Okay. So usually if you use RB like say 10 mega ohm, okay, so you can achieve maximum resistance of the order of say 100 mega ohm or so. Okay. You cannot go beyond that kind of resistances. Okay. So this is a multiplication factor, and this is very crucial for designing such kind of, this can assist such kind of capacitive sensor. This is very important, particularly for sensors which are charge generating, okay, or say current generating sensors. Okay. It basically it can be used for both capacitive sensors as well as for non-capacitive sensors also. Okay. But of course, the sensor should be a current generating sensor. Okay. So that's all for this lecture. We will again continue this interface circuit discussion in our next lecture or the third lecture. Thank you for attending this class.